Hi, welcome back to Statics 1. Today we're going to talk about something called the dot product. It's a way of multiplying two vectors and coming up with a scalar. It has some really interesting properties and a couple different applications that we'll talk about. You might remember we talked about this, or at least I mentioned it, back when we were discussing the multiplication of scalars and vectors, which, as you know, if you have a scalar that's greater than 1, you multiply it by a vector. The vector stays in the same direction, but its magnitude is lengthened. Okay, in this case, we have something very different. And so I'm going to first I'll give you the definition of the dot product, and then I'm going to show you how you actually implement it. And then lastly, we'll talk about some applications of the dot product. Okay. So, what we're talking about is the dot product. And why do they call it a dot product? It's because when you multiply two values, we use a dot to as the operator. A dot B, right, equals A B, where these are the magnitude of these vectors times cos theta. What we're looking at here, two vectors, A and B, with an angle in between them. Okay, and A dot B, B dot A, same thing, because you're just reversing these, so you get the same value. The cos theta, is the same. All right, so this has some interesting properties. Let's look at the unit vectors I, j, and k, and what happens when you multiply them by each other. If you have I dot I, for example, okay, so we're going to take the dot product of two unit vectors. They're essentially the same vector. The value of theta in this case, of course, will be 0, and cos 0 equals what? 1, right? So I dot I equals the magnitude of I, which is 1 times cos theta, which is 1. So that equals 1. All right? So I dot I equals 1. Likewise, j dot j equals 1. K dot k equals 1. I write that here just so we remember it. J dot j equals k dot k equals I dot I. And that's how you say this, by the way, I dot I. And the reason you say that, you don't just say I times I, is because we're going to have another way of multiplying vectors called the cross product. In that case, we're going to say something like I cross I or I cross j. So it's different. So you need to distinguish between those two ways of multiplying. All right, that's good. Now, what if we multiply I times j? So it would be like I vector and a j vector. Both of these, of course, being unit vectors. They have magnitude of 1. But in this case, we have a theta value of 90 degrees. Cos 90, what is it? 0, right? So I dot j equals 0. Likewise, any two of the unit vectors, I, j, k, multiplied by any other unit vector, so it would be also equal to 0. So I dot j equals 0. I dot k equals 0. K dot I, what? 0. K dot j, 0. All right, so this has an important implication when we actually expand this. This has an important implication when we expand the vector in the way I'm going to show you in a second. Now, what I'm going to do is I'm going to take this A dot A, and I'm going to write it as AXI in our standard Cartesian form. And I'm going to do it right here. AXI plus AYJ plus AZK. All right, that's my Cartesian form of A vector. Now I'm going to do the same for the B vector. And I'm going to put a dot here because we're taking the dot product of the two vectors. And hopefully it's going to fit. I'm going to have to write a little smaller. Hopefully you can read it. Make sure you're looking at this full screen. bxi plus byj plus bzk. Made it. All right, so what is that going to equal? The dot product has the property of distribution, just like multiplication. So we can expand this by multiplying this times that times that times. We can multiply this times this and add it to this times that one times that. You get the picture, right? We can multiply all these values. You end up with 3 times 3. You end up with 9 values. And I'm going to do first the ones where the unit vectors are the same. So what I'm saying is I'm going to say ax, this is equal, basically this term is equal to this term, ax bxi dot I plus ay by j dot j plus az b z k dot k. Now we can take all the other terms where the unit vectors will be different, like axi times byj. I'm going to write it down. So we add it here, ax by I dot j. What is I dot j? We already said I dot j equals 0. So this term goes away. And in fact, all the other terms are going to go away because they're all going to be dot products of either I dot j, j dot k, I dot k, where the unit vectors are different and have an angle of 90 degrees, so that cos theta in the dot product makes them go away. So this, in fact, is the expansion that we're looking for, and we can actually replace, we know that I dot I, j dot j, k dot k equals 1. So we can replace this by ax bx plus ay by plus az bz. So that is what a dot b looks like. So I'll write it here. A dot b equals that term here. Right, so that's the relationship we're looking for. So if you want to evaluate a dot b, you take the vectors, you can evaluate that, and that's going to be equal to the magnitude A times the magnitude of B times cos theta. Now this is going to give it, this as two important applications, one of which, and I'm going to write them, how am I going to do this? I'm going to erase the board, and then I'm going to come back and I'm going to talk about those two important applications of the dot product. So what I want to talk about now is the first application of the dot product, which is to find the angle between two vectors. Now in 2D, it's not a real big trick. We can do that without using a dot product. But in 3D, frequently, and we could even do in 3D, we can use geometric, trigonometric relationships to find angles. However, it's a lot easier to do it using this approach. So what I'm going to show you is how we do that. So imagine that we have two vectors, A and B, and they could be coplanar or they could be in 3D. In other words, they could be in different planes that are not in the XY or YZ plane. And what we do is we're going to equate this. So A dot B equals A times B times cos theta, where these are magnitudes. And that's equal to the expanded dot product of the vector. So what we're going to do is I'm going to equate these two values, and I'm going to put cos theta on the left side. So I'm going to say cos theta equals ax bx plus ay by plus AZ BZ over the magnitude of A times the magnitude of B. And you know, to get the magnitude of A and B, that's just we use the Pythagorean theorem, right? It's the square root of AX squared plus BX plus AY squared plus AZ squared. That would be the magnitude of A. And the magnitude of B is the same square root of BX squared plus BY squared plus BZ squared. All right. So these are all known quantities. If we knew the vector A and B, but theta was unknown, these are known quantities, and we can apply the arc cosine here, or the inverse cosine, which will just give us theta. So we'll have theta on this side, and on this side we're going to have arc cosine of this entire term, and I'll rewrite it in here. AX BX plus AY BY plus AZ BZ over the magnitude of A times the magnitude of B. All right, so if we knew the vector A and B, we knew the Cartesian form of the vector, we would know everything here. We would apply the arc cosine function, like the inverse cosine function, and that'll give us the angle theta between those two vectors. So in a minute, I'm going to show you next an application of this, quick application, just show you kind of the utility of this technique. So give me 1 second to set that up. All right, so hi, so I'm back. So what I'm going to show you is an application where we're going to use the dot product to solve for the angle between two vectors, okay? In this case, we're going to have one vector extending from, here's a 3D case where we have points C, A, and B. And in this case, we have a force vector pointing from A to C. And you can see the coordinates. We have 4 meters along the x-axis, 3 meters along the y-axis, and 4 meters along the z-axis to the B. So what we're going to want to find is the angle theta between this vector and that vector. All right, easily done. And what we're going to do is we're going to write position vectors between here and here, and a position vector between here and here. We'll find their magnitudes, and then we will apply our dot product and solve for the value of theta. So let's see if we can do it. All right, so first I'm going to do R of AB. It goes in the y direction, it goes -3, and the x direction is 0, and in the z direction is a +4. So we have R A B equals, it's going that way. So there's a -0 times I. I'll write it out. 0 times I. I was going to leave that out. -3 times J, right? Because it's going 3 in that direction, then 4 in the K direction. And these are in, this is a 0, by the way. This is all in meters. Okay, that's RAB. And can we find the magnitude of RAB? Square 16. Oh yeah, this one's going to be easy. So the magnitude of RAB right here equals the square root of 3 squared, 3 meters squared plus 4 meters squared, which is 16 plus 9, 25. So this equals 5 meters. Great, that was easy. All right, let's do this one from A to C. So we have RAC equals RAC. Oh, this is a vector, by the way. Never forget your little arrows. Let's see if I forgot any other ones. Nope. RAC. Okay, so where does this one go? It goes in the x direction. It's going to go a +4. So we have 4 times I. In the y direction, it goes -3. -3J. And in z direction, there is no value. Okay, plus, so it's 0, K. Again, this is in meters. And then look here. So it's the same as before. We're going to have a 4 squared, which is 16, plus 3 squared is 25. So I'm just going to write the result here. Hopefully you won't mind that. RBC equals 5 meters. All right, we're almost done, believe it or not. Now we're going to express it in this term. And the interesting thing is that where we have a 0 in this vector RAB, we have a positive value. In other words, for the I vector term, for the K vector term, we have a 0 here. So this term and this term are going to go away. We're only going to have the middle term, the negative 3 times the negative 3. So I'm going to write RAB. Actually, I'll write this entire function here. Let me do that. Excuse me. So I'm going to write theta equals arc cosine of, and as I said, only the middle term is left, which is negative 3 times negative 3 meters. So that's 9. It's negative 3 meters times negative 3 meters, right? And then divided by the product of the magnitudes. So each of these magnitudes were 5 meters. So we're going to have 5 meters on the bottom times 5 meters. All right, so there we have it. So this is going to be 9 over 25. So we're going to take the arc cosine of 9 over 25, and we're going to get an angle. I'm going to pause the video, and then I'm going to write the answer. And then we'll see if it looks reasonable. It looks like it should be something, well, I don't know. I'm guessing about 70 degrees. But let's see what we get. So I'm going to pause the video now, and I'll do some calculations. Hold on. All right. Okay, I'm back. I did my calculations, and believe it or not, I was almost exactly right, and it's equal to 68. Hold on, let me see again so I get the right number. 68.90 degrees. So 68.9 degrees. All right, so it shows how easy. This is like a complex geometric problem, but it reduces to kind of a very simple problem when we apply the dot product. So that is application number 1, finding the angle between two vectors. Application number 2 is going to be finding the projection on rectangular coordinates, and I'll explain what that means in a minute after I clean up the board. All right, hi, I'm back. So I want to talk about the other application of the dot product, which is to find the rectangular components of a vector. So what do we mean by that? I mean, we talked about components before, where the components are basically two vectors that summed up result in some other vectors. So we had sort of a very general case, and we looked at these earlier in the term. We had some vector, like, we had some vector, let's just try there. Okay, so we had some vector like that, and we said, what are the components along two other lines? And in these cases, these lines weren't necessarily perpendicular to each other, but we called this the resultant vector. Resultant vector, and we called this one over here, we called this the component vector. Remember, we used the parallelogram law. Let's see if I can do it. So we had a vector here. I'll do it in blue, our components. So here's our component vector number 1 over here. And then we have another component over here. And these are basically, so it's like vector 1 plus vector 2 equals vector R our resultant vector. This is our resultant vector. Here's a vector 1, vector 2. We call these the components of that vector. And you can do it from any angle. But you may have, there's a kind of a special case, which is when this angle equals 90. And it may be aligned with the xy axis, but it might not. It might be aligned with some other axes. Under those situations, under those conditions, we can use the dot product to do that very easily with very little effort. So let me show you that. Actually, what I'll do is I'll draw it here, and I'll draw our essentially, we want components of some vector. So here's my vector v r. That's my resultant vector. And then I want the components along these lines. And let me erase those arrowheads. So we'll just show these as lines. And we want to find the components along these lines. And these lines happen to be perpendicular to each other. And these components we call projections onto the line. So projections of this force vector onto the line, you're going to find the rectangular component along this line and along that line. All right, so how do we do that? It's actually quite easy. So what we're going to do is we're going to define position unit vectors along each of these lines. So I'll call this one in this direction unit vector A, and this is line A. We're going to call this line B, and these lines are, line A and line B are perpendicular to each other, and I'm going to define another unit vector in this direction, which I'm going to call U sub B. So unit vectors, remember, unit vectors, remember, have magnitude of 1, right? What we're going to do is we're going to take the dot product of VR and UA, and you're going to see some interesting things shaking out about that. All right, so we have VR dot UA. All right, what you're going to end up with is we're going to use this relationship. So in our case, A is now VR. So we're going to end up the magnitude of VR times the magnitude of our unit vector, which is what? 1, right? So I'll just leave it out. And then you're going to have cos theta. So VR cos theta, that's like our trigonometric relationships. That's going to tell us exactly what is the magnitude of that vector, the component that's going to tell us the component in the A line direction of our vector VR. And that's a good thing. And how do we evaluate that? We can just use this term here. So we're going to end up with VRX times UAX. In other words, VR, the x component, times UA x component, plus VR y component times U a y component plus VR z component times U a z component. Okay, so if we know the vectors, and we know how to find a position vector along this line, and we know the v sub r, then we can evaluate this, and that'll tell us what that in the A direction projected onto the A line. So that's what it's telling us. So it's giving us the projection of VR on line A. Okay, so that's number one. Now what if we wanted to also have the projection of VR on line B? So in this case, we're not going to apply the dot product. You could apply the dot product and evaluate for another value of theta, but it's actually an easier way of doing that is to realize that VR equals VRA So vector VR equals VR projected onto line A plus that other vector. So remember our triangle rule. So that's going to give us our VR value projected onto line B. So we have to add these together. We know this vector because that was a given from the problem, typically. We know this one because we evaluated it up here. That's what this is giving us. This is the actual quantitative value. We don't know this one, but we know how to subtract vectors in Cartesian form. So VRB equals simply VR minus VRA. So I've just rearranged it. So we're going to solve for VRB, essentially the component along line B, which is perpendicular to line A. So in doing this, what we've done is we found the components for lines that are at right angles. So it's a particular form which is advantageous. So sometimes you may have a case where you want to know, for example, you have like some kind of a pipe, say, and you have some kind of a force applied, and you want to know how much of that force is perpendicular to my pipe, and how much of that force is going to be parallel to that pipe. So that would be an important application that you might imagine for doing this procedure to finding the projection. So you'd have a force. Here's your force. And this would essentially be what we were calling the projection onto A. So we'd have F of A on line A, lowercase a. And this would be F on lowercase b in the perpendicular direction to A. So that's their two applications. So remember that the two applications of the dot product are, if you're in the room I'd ask, but they are, number one, finding angle between two vectors. So I'll just draw a little picture here. So that's number one, A, B is theta. And number two is finding the perpendicular components. And that would be, in this case, if you had a force like that, and you want to know components along lines that are perpendicular to each other. So the perpendicular components, those are the two applications of the dot product that you should be aware of. So if you have any questions, this one's a kind of a complicated topic, I think. If you have any questions, bring them up in class, send me an email. And I think we'll have some homework problems, especially related to this finding the perpendicular components. So rather than showing you an example, now we'll leave that to in class. So we'll talk then. I'll see you in class.